Now, in our previous examples, we cut our members at some angle, and we note that our average normal and average shear stress is going to be dependent upon this angle. If we look at our member in a two-dimensional system, we can define the following. We can say the magnitude of our normal internal reactionary force, R sub n, would be equal to the magnitude of our internal reactionary force, R, times cosine theta. Our transverse or tangential component of our internal reactionary force, R sub t, would be equal to R sine theta. And our shear area would be equal to cross-sectional area per cosine theta. Therefore, we can redefine our average normal and our average shear stress based upon theta. First, we'll look at our average shear stress. Our average shear stress is R sub n per A sub n, where R sub n was R cosine theta and A sub n is A per cosine theta. This gives us a quantity R cosine squared theta per our cross-sectional area, which can be expressed as R times the quantity 1 plus cosine 2 theta per 2 times the cross-sectional area. Our average shear stress is expressed as R sub t, which is our transverse or tangential internal reactionary force per A sub n. R sub t is equal to R sine theta, and A sub n is A per cosine theta. This is equal to R sine theta cosine theta per our cross-sectional area, which is equal to R sine 2 theta per 2A. Now, if we plot our average shear stress and our average normal stress versus theta, where theta goes between 0 and 180 degrees, we can determine our maximum and minimum values. If we look at our average shear stress, which is denoted as the blue line, we have a maximum value when theta is equal to 0 degrees or 180 degrees. This means when our plane is mutually orthogonal to the axis that defines the center line of our member, we'll have a maximum normal stress. And our maximum normal stress is simply R per A. Now, when we plot our average shear stress, we see we have a maximum at 45 or 135 degrees. That is, we can say our maximum shear stress is R per 2A when we substitute in these values into our previous expression. We note that our maximum shear stress is always 1/2 of our maximum normal stress. Now, it is noted that we don't have to actually cut our member. Rather, we'll only take the maximum normal and maximum shear stress values when analyzing our component. To see this in application, let's consider a situation where we have two pieces of wood that are glued together at a scarf joint. Our scarf joint is measured 40 degrees above our horizontal plane. A load of 2,400 newtons is applied to both ends of the system. If our wood structure has a cross-sectional area of 800 centimeters squared, we want to determine the normal stress in the glued joint. To solve this problem, we have to recall our angle theta is going to be measured with respect to our vertical direction. Thus, theta is going to be 90 minus 40 degrees, i.e. 50 degrees. We can solve for a normal stress based upon our normal force R sub n and our area A sub n. That is, our average normal stress is going to be R sub n per A sub n, which is R cosine theta per A per cosine theta, which is equal to R cosine theta squared per A. When we substitute in our values, our internal reactionary force is going to be 2,400 newtons. Our cross-sectional area is going to be 0.0800 meters squared, and cosine theta gives us a value of 0.643, and we'll take this quantity squared. Thus, our average normal stress is 12.4 kPa.